So in this video, we're going to look at continuity and differentiability. Does continuity imply differentiability, or does differentiability imply continuity, um, or is it both ways? So that's what we're going to look at here. We want to consider this function that's given, and you want to, on the grid to the right, you want to graph that function from your graphing calculator. So you can pause it, get it on your graphing calculator, and come back and see if it looks like mine. All right, so this is what your graph will look like. Based on that graph, we want to talk about, is this function continuous at x equals 2? We want to explain our reasoning. So the three criteria of continuity, this is a good review for us. First of all, is f of 2 defined? It is defined, and its value is 0. The second criteria, does the limit exist as x approaches 2 of f of x? And the limit does not exist. So why would that not exist as x approaches 2? Well, the limit from the left does not exist because there's no graph to the left of 2. So that makes us say that the limit as x approaches 2 from the left does not equal the limit as x approaches 2 from the right. So therefore, the limit does not exist. And again, that's because the limit from the left doesn't exist because there's no graph to the left of 2. All right, so criteria 3, just as a reminder, would be, are those two things equal? But of course, if the second one doesn't exist, then of course they're not equal. So we can say, therefore, the graph is not continuous at x equals 2. So we've discussed the continuity of that graph. We want to see, is there a relationship between continuity and differentiability? Does one imply the other? So now we want to look at, is the function differentiable at x equals 2? So we can take the derivative of our equation. So they want us to they want us to do it without looking at the graph, but to do our derivative. So this is a chain rule problem. So I multiply by, that 2x is coming from the derivative of the inner function. So now I'm just going to evaluate by plugging in 2 for x and see what value we get for our derivative. So that negative exponent is going to really put it on the bottom of our fraction there. So that's why we're getting 0 to the 1/2 on the bottom. And so that's going to give us a 0 in the denominator. So we end up getting 2 over 0. That means that that number is undefined, which means the function is also not differentiable because my derivative is undefined at that x value. So f of x is not differentiable. So in this example, f is not differentiable and not continuous. All right? And so, of course, we say it's not differentiable because the derivative at 2 is undefined. Graphically, what does it mean? Why does it not have a derivative? What's going on there to make it not differentiable? So let's look at the point 2. How do I draw a tangent line here? I could draw it several different ways. There are infinite tangent lines I could draw at that point. So if there's not a unique tangent line that can be drawn, then we say that the function's not differentiable. It's differentiable if I can draw a single unique tangent line at any given x value. All right, so we're just going to write out that explanation, that graphically it is not differentiable because there's not a unique tangent line that could be drawn. So I already made this video and the audio didn't record, so now I'm just sort of watching it and re-recording the audio over the top. So sorry if it doesn't flow exactly right, but we get the point here. All right, so in that first example, it was not continuous, the function was not continuous and also not differentiable. Let's look at another scenario. So again, you can pause it here and try to sketch a graph from your calculator. You should get a graph of something like what I drew here. So now we're going to do continuity. So again, is f of 0 defined? And if it is, what's its value? So it looks like it's 2. Now the limit, does the limit exist as x approaches 0? And it looks like it does. So that's because the limit from the left is approaching a height of 2, and the limit from the right is approaching a height of 2. So the limit definitely exists because the limit from the left equals the limit from the right, and they're both equal to 2. So their value is also 2. So then criteria 3 is the function value equal to the limit as x approaches 0? So yes, the function at 0 is equal to the limit, which are both equal to 2. So therefore, the function is continuous at x equals 0. So again, good review of our continuity definition. So find the value of f prime of 0. So they want us to actually do the derivative out, plug in 0, and determine if it's differentiable. So I do power rule to get 1/3 x to the negative 2/3. So I rewrite so that the power is not negative. I plug in 0 into my derivative, and I get 1 divided by 0. So that is, again, undefined. So that means that f of x is not differentiable at 0. I know that because the derivative, when I plug in 0, it becomes undefined. What is that? What happens? What's happening graphically here? It's not that idea that I can't draw one unique tangent line on the graph. So we want to look at why is it not differentiable on this graph? There is only one tangent line at 0, but remember that derivative means the slope of that tangent line. So vertical lines have a slope of undefined. So anytime our tangent line goes vertical, that's another reason why I might have an undefined derivative. So that's what's going on there. So you can see that if I draw tangent lines leading up there, I have all my unique tangent lines leading up to the point 0. When I get to 0, the tangent line goes vertical, and the slope of that line is undefined. So that's why it's not differentiable. So now we have a function here where it's continuous but not differentiable. So we found a counterexample. In example 1, we had a function that was not continuous and not differentiable. In example 2, we have a function that is continuous but not differentiable. So we found a counterexample. That means that continuity does not imply differentiability. Just because a function is continuous doesn't make it differentiable. However, not does imply not. If the first example showed us that if a function is not continuous, it's not differentiable. Because if a function is not continuous at an x value, how the heck could it even be differentiable? I can't draw a tangent line if there's not continuous. Let's look at this next function. So that's what the graph of this function looks like. So based on the graph, let's check for continuity. And you should pause the video here and do this and see if you can do the continuity yourself. All right, so welcome back. Here's what I got for continuity. You can pause it and check your work. We found that the function is continuous at 0. Now let's look at the differentiability of it. Let's, not from the graph, but from the equation, let's take the derivative, plug in 0, and see what kind of derivative we get. What is the slope of the tangent line? So again, it's undefined. When I do power rule, I plug in my 0. I'm getting an undefined slope, so that means that f of x is not differentiable at 0. So here's yet another example of a function that's continuous at an x value, yet not differentiable. So clearly, continuity at a point does not imply differentiability. Just because a function is continuous does not mean it has to be differentiable. I will tell you that the other way works. If a function is differentiable, it must be continuous. So differentiability does imply continuity. So if we look at this graph, why is it not differentiable now graphically? We know we got undefined for slope. Again, we can draw more than one tangent line here. So what's happening on this graph is that I've got what's called a cusp or a spike. It's like a sharp point. The graph is not smooth. It's not a smooth curve. So again, not there. I can't draw a unique tangent line here. I can draw more than one tangent lines at that x value. So since you cannot draw a unique tangent line, graphically we would say the function is not differentiable there. Okay, so I'm looking at like another type of graph here, like a piecewise graph where it might not be a smooth transition where I can't draw one tangent line. Like this piecewise graph here can create a corner where I can draw more than one tangent line. Even though the function's continuous there, I have a corner or a sharp turn. That's a spot where you might not have a differentiable function. Okay. Now some piecewise functions will be differentiable. If like that first one I drew, maybe it's like a nice smooth turn and it doesn't make a sharp corner. So maybe I can draw a unique tangent line. But graphically, when this happens, we call it a cusp, which means it comes to a sharp point. And that means that I can draw more than one tangent line. So therefore, it's not differentiable. So the thing to stress here is, again, that continuity does not imply differentiability, but differentiability will imply continuity. We haven't really proven that yet, and we'll talk about that in class. So based on what we've seen, does continuity imply differentiability? The answer is no. Continuity does not imply differentiability, but differentiability does imply continuity. So I'm writing this out, what I've said a couple times now and what it means. So you do want to get this written down. It's kind of weird the pen is skipping. All right, so that's that continuity does not imply differentiability. However, vice versa is true. We haven't really shown why, but we will. So continuity doesn't, but differentiability does. That's why I'm underlining it here. Said that a couple times now. Sorry. It goes a little more smoothly when I'm actually writing and talking at the same time. This is annoying that I had to do this and then record the audio over it again. All right, so now we're looking at, if I drew like a clearly a not continuous graph, of course it's not differentiable there. How would I draw a tangent line at that spot where there's a jump in discontinuity? You can't draw a tangent line there. If the graph like separates, it's got to be continuous for it to be differentiable, to even have a chance. And even if it's continuous, it doesn't have to be differentiable. So two things have to happen. Number one, the function has to be continuous in order to even have a chance to be differentiable. That's criteria one. F of x must be continuous in order for it to be differentiable at an x value, say a. The second thing that happens is the way we can talk about this cusp, there's an official kind of math definition to it too, where the derivatives of the tangent lines sort of make a smooth transition, and it's not just a jump from one to the other where I can draw many. The limit of those derivatives from the left has to equal the limits of those derivatives from the right. So I'm not talking about the limits of f. I'm actually talking about the limits of those derivatives. Those slopes of those tangent lines have to be approaching the same number from the left and from the right. So that would mean that the limit of the derivatives exists. That's how we know that there's not a cusp, that it's a smooth transition. Again, we can talk more about this in class. That will avoid the whole like I can draw more than one tangent line. If the limits of my derivatives, right, if those limits of my derivatives are approaching the same value from both sides, then I'm going to have a smooth curve there. There's not going to be a corner or a sharp point where I can draw many. So again, I'll show you what that means in class. So you pause the video here, and I was saying that you want to show that this function is continuous at 3, so you can pause it and see if you know how to do that there. So now we're going to look at how do we tell if it's differentiable, the piecewise function. So we're going to have to take the derivative of it. All right, so we just showed above that it's continuous. So we got criteria 1 there. And then step 2, to show it's differentiable, we want to show that the limit of the derivative from the left is equal to the limit of the derivative from the right. So we're going to have to take the derivative of that piecewise function. So we're going to recopy our piecewise function here. What's up, Hankies? So we've got x plus 1 to the 1/2 from 0 to 3, and then 5 minus x from 3 to 5, was it? So now we're going to take the derivative of that function, and you can just take the derivative of each piece. So this is going to be a chain rule. The 1/2 comes down, recopy the inside, reduce the power by 1 times the derivative of the inner, and then it's on the same interval from 0 to 3. The derivative of 5 minus x is -1. So if I rewrite, I've got 1 over 2 times the square root of x plus 1 from 0 to 3, including 3, and then -1 from 3 to 5. Oops, I got to write the x in there. So now that I have my derivative, I can check the limits. Sorry, not very inspiring if I'm yawning while I'm doing the video. All right, so from the left means if I take that derivative, I'm going to plug, which one means from the left? The x's that are less than 3. So if I plug 3 into that top equation, I'm getting the limit, or what I'm approaching, my derivatives are approaching from the left. So I use the top one to check from the left, and then from the right, that's the x is bigger than 3, so I plug 3 into the bottom function, I get -1. So therefore, the function is not differentiable because criteria 2 was not met. The limit from the left does not match the limit from the right of the derivatives, right? So the limit as x approaches 3 of g prime of x does not exist. That should be a g prime of x, not a g of x. I'm finding the limit of the derivatives because the limit from the left of g prime of x does not equal the limit from the right of g prime of x. And again, I need to put a prime on that first limit. So therefore, the function is not differentiable at x equals 3. Okay, so we're going to move on here and we're going to find a k and an m such that the function is both continuous and differentiable. So for the function to be continuous, remember the limit from the left of h has to equal the limit from the right of h, and for it to be differentiable, the limit of the derivatives from the left has to equal the limits of the derivatives from the right. So those two things have to happen, so we're going to make both of those happen. So first, for continuity, the limit from the left of h has to be equal to the limit from the right of h. Why did I put a -1 there? It's just minus means from the left. From the right. Okay, so I plug 3 in. For x is less than 3, coming from the left, I'm on x is less than 3, the top equation. I plug 3 into the top, and for coming in from the right, I take the x's that are bigger than 3, so I use the bottom equation and plug 3 in for x. So I'm going to plug my 3 in for x in the top, and I get, after I simplify it, I get the square root of 4, which is 2. I get 2k equals the limit from the right. We'll be plugging 3 into the bottom function. I'll get 3m plus 2. So now this equation has two variables in it. So I need another equation to help solve this equation, right? I need a second equation so I can solve the system for k and for m. So there's my first equation. My second equation is going to be, this is to prove that they're continuous, or for them to be continuity, those limits, continuous, those limits have to be equal to each other. Now for the differentiability, if I make the limit from the left of the derivative equal the limit from the right, then the function will be differentiable. I already know it's continuous because I'm forcing it to be continuous from the top part. Now I just got to force it to be differentiable. So now I need to go take the derivative of that piecewise function. So I do chain rule, the 1/2 comes down times the k. Remember, you're just treating k as a constant to the negative 1/2 power, and then I multiply by the derivative of the inside, which is 1. So then the derivative of mx plus 2 is just m, because m is a constant. I rewrite the top one and simplify it to k over 2 times the square root of x plus 1. And now I can do the limit from the left and the limit from the right of the derivative. So if I plug 3 in for x to the top, I'm getting k over 4. And if I plug 3 into the bottom, I just get m. So I'm getting k over 4 equals m. All right, so there's my second equation in my system. If I pull both of those equations together, 2k equals 3m plus 2, and combine that with the other equation in my system, which is k equals 4 times m, so I'm just multiplying both sides by 4. I can do some substitution here and plug 4m in for k into that top equation. So I'm rewriting the top equation, plugging in 4m. I can solve that for m, and I'm not going to work that out here on the video. You'll get 2/5. Now I can substitute that back in for m and get k. And again, I'm not going to work it out. You can figure that out. K is 8/5. That's an m and a k that will make the function both differentiable and both continuous. This guy is the same exact question. So you should pause the video and try to do this one. So the first thing is we're probably going to need the derivative. Oh, yeah, so here you go. Here are the answers. So we're going to need the derivative. So first I'm actually going to do the derivative, and I simplified it a little bit, treating a and b as constants. So I did power rule, bring the 2 down, I get 6ax, right? I did so. You got your derivatives there. You can pause it and look through them. So for continuity, I want to make the limit of f from the left equal limit from the right. So if I plug 1 into the top function, and then 1 into the bottom function, I'll get my limit from the left and from the right, and I'm plugging them into x, so I'll have a's and b's left. If I simplify that equation and turn it into a standard form, you should end up with 2a plus 6b equals negative 4. Again, I urge you to pause this and do this. You should have worked this out already. Now I want to do the differentiability one, where I know the limit from the left of the derivative should be equal to the limit from the right of the derivative. So I'm going to take my derivative function and plug in my 1 for my x's up top, and that'll be the limit from the left. Plug in the 1 for x's in the bottom equation, that'll be my limit from the right. Simplify that equation and put it in standard form. I get 2a plus 10b equals negative 3. I pull both of those equations in standard form together, and I can solve the system. Elimination is going to work here, so I can multiply one of those equations by negative 1, eliminate the a's, solve for b, go back, substitute, plug the b in to one of the equations to solve for a. These are the two solutions that you should get together. So a is that, and b is